The homework notebook doesn't have to be a SOM-bound composition. It's just nice to have something like a comp notebook for that, so it's all in one place. And you don't have to worry about if, when you turn it in, I'm going to give it right back to you, so you don't have to worry about tearing out sheets and then submitting a homework assignment. Just submit the entire notebook. You don't. The homework notebook's not a requirement. You know, I just prefer to just see homework notebook instead. The lab notebook is required. All right. So for the first page or two, let's do. Do you write on both sides or one side of the? A lot of people want to save space, so they'll write on both sides. But normal practice is just to write on one side of the page. You can scribble notes on the other side. And so just the first 2 pages, you know, you want to reserve for a table of contents. So we'll just call it page 1. Actually, you might only just need 1 page for the table of contents. Table of contents. And then we're going to start with page 2, or notebook. All right, like I said, today's lab, you're going to put all the original data onto the report sheet and hand in the report sheet later on. That's okay. You lose Experiment A's original data you've given to me, and it's okay if you don't have it in your notebook. How many people have a notebook? I know Cecilia, just a few of you, 2 of you, I think, 3. All right. So by Thursday, bring a notebook. Make sure you stop and get one. And then here we're going to start with experiment 1B. Experiment 1B, sulfate analysis. You know, the title is something else, but you can just sum it up as sulfate analysis. And, you know, just a short description. You just copy the purpose. You know, what is the purpose of the experiment? It's a good idea to have that known. You know, at UCLA, also UCSB, pre-lab quizzes were common. One of the common questions on pre-lab was, what's the purpose of the experiment? You know, most people get it wrong once and then quickly learn. They need to know what the purpose is before coming in to lab. But the purpose for this experiment is we're going to analyze an unknown solid for sulfate content. Basically, analyze, you could use this if you want. Analyze an unknown solid. For sulfate content. Then what we'll do is we'll divide this, you know, maybe 2/3 of the page. You don't have to follow this format. You know, there are other formats you can use. But for this first lab, I just recommend trying this. On the left side of this, we'll put the not the purpose, we just wrote that, the procedure. And on the right side, we'll put the observations. So what's the difference between procedure and observations? Stanley? Saw your hand move, but it was just scratching your head. It's okay. Okay. No, you're well. That's good. I mean, that's good because that's a scientific method. But observation, you're going too far here. Procedure is what you're supposed to do. Observations are what you actually did. Okay, data analysis, data reduction is you're looking for patterns. You know, normally you took it one step farther. Observations, well, let me just emphasize this point. Let's say the procedure says to weigh out 10 milligrams of manganese oxide. You're at the balance and you put in 14 milligrams. Are you going to take some tweezers and take out 4 milligrams worth of manganese oxide off the balance and put that back in? No, you're just going to say, well, you weighed out how much? You weighed out 14 milligrams. So the procedure said weigh out 10 milligrams, you got 14 milligrams. In your observation, you write 14 milligrams. You know, and the procedure, for example, we're going to modify the procedure. I'm going to talk about Thursday's experiment since Thursday is a busy day. And so this is going to be the pre-lab for Thursday. Normally pre-lab we can do on the same day, but the analysis goes like this. There's something called a weighing bottle. And this experiment was written for old style balance. You know the old balances, you know what the maximum you could tear is? Well, first, what is tearing a balance? What do you do when you tear a balance?
Cancel out the container that you're using.
Or you just, essentially it's not just the container, but there's a pan, a metal pan, and other things on the balance. And you make sure those are all reading 0. And so initially when we use a balance, we'll tear it. And the old style balances, you couldn't tear a container. You know, all you could do is you could tear the weight of the pan, as they weren't as flexible as modern day balances. Modern day balances, you could tear heavy objects like a couple of hundred grams and just set it to 0. And so, I got it. So, actually, maybe in a few minutes I'll talk about this. But, so this procedure is written for something else. The old style balance. Old style balance is we have our unknown sample here. And normally what you did in the old days was you weighed the bottle and the sample. And then you tap some of your sample into your container and then re-weigh the bottle and the sample. And the difference is how many grams of sample you got inside your container. Now, in experiment 1B, what we're going to do is we're going to get 3 beakers. We're going to do 3 trials. And we need to weigh out three samples of unknown. The easiest way to weigh out 3 samples of unknown is, even with a big beaker here, we could zero the balance with this beaker by hitting the 0 or the tear button. And so we hit the 0 button, and then instead of weighing the weighing bottle, we don't need to know how much the weighing bottle weighs. All we do is we remove the lid on the weighing bottle, and then go over to the balance, and then just tap in our sample. get it to as close to the mass as you require. But what if you overshoot by a little bit? If you overshoot by a little bit, that's okay. Now, if you overshoot by a lot, that's probably not good. If you undershoot by a little bit, that's okay. What kind of tolerance do we have for undershooting and overshooting? Well, we don't want to go more than 20% one way or the other. You don't want to undershoot by more than 20%. You don't want to overshoot by more than 20%. And so whatever the desired mass is, let's say the desired mass is 1 gram. That means anywhere from what to what is okay. Anywhere from 0.8 to 1.2, because that's within 20% of 1 gram. Okay, even though it says, anywhere in that range is okay, when we take our observation, do we want to write down all the digits the balance gives us or just some of the digits? The balance is going to give us a lot of digits here. It's going to give us 4 decimal places. We call it a tenth of a milligram. Because here, the first decimal place is called a tenth of a gram, or centigram. And so we have centigram balances. Oh, actually, no, that's a tenth, is not a centi. A centi is what? 100. And so the first decimal place is a tenth. The second decimal place is a hundredth, which is a centigram. A centigram balance is what you used in Chem 4. It's only 2 decimal places. But we want greater precision, because we can't get the level of precision desired with those centigram balances. So we're using not a milligram balance. A milligram balance would be 1,000th of a gram. We're using a tenth of a milligram balance, which is 1/10,000th of a gram. Here. These balances are 5,000, actually more probably now, dollars each. So be gentle with these balancers. They're very expensive. If you weigh to the nearest tenth of a milligram, we have a problem with sensitivity. If somebody walks by the balance, they create a little wind current, right? And that wind current is going to cause this to fluctuate. You aren't going to get a stable mass. It's going to be very frustrating. To block out those wind currents, this whole balance is encased in a plastic box. There are 2 sliding doors, depending on what. If you're right-handed, you could use the right-hand sliding door. And the sliding door you can open and close. So you open it, set your beaker on there, close it, and then tear it. There's also a left-handed door. Left-handed people. But, a tenth of a milligram balance is so sensitive, you know what? It can weigh fingerprints, fingerprint residue. And so you have to be very careful about that, because if you keep touching and the beaker, you're leaving residue on that beaker, which is going to affect the mass of the beaker. And so you have to handle these with either a paper towel or tongs or something else, something that's not going to leave residue. Be careful of the tongs, though, because a lot of our tongs are rusted. You don't want chips of rust falling into your unknown or onto the balance pan, affecting the mass. Not only that, these balancers are sensitive enough to pick up humidity that's absorbed by the sample. So if you have a dry sample, it's kind of humid today, right? And that humidity is going to saturate the surface of the sample, because a lot of these, just looking at a salt, salt consists of a cation, an anion, in some kind of, what do we call this structure?
Lattice.
In some kind of lattice. There's going to be a surface on this structure like this. And then we have water molecules in the air. Zipping by, these water molecules. But some of them will strike the surface. If they strike the surface, what can happen? They can bounce off, right? Or they can get stuck. If a water molecule strikes the surface and gets stuck, what's holding it? What's holding the water molecule to the surface? This. Well, what's the primary force in chemistry?
Electrical charges.
Electrical forces. So what's holding the water molecule to the surface? Electrical attractions. What's the electrical attraction between a water molecule and the surface of a salt? I'm sorry? Yeah. It's what we call an ion dipole attraction. Water is a dipole. You know, there's a delta minus and a delta plus. Are you guys familiar? Obviously, you're familiar with this, right? Water is very polar. And so the delta minus is going to be attracted to the cation. So if it gets stuck here, the delta pluses would get attracted to the anions over here. And so the surface of this can get saturated. Sometimes if there are big void spaces, the waters can get incorporated within the crystal structure itself. We call those hydrates. You heard of hydrates in the intro? Where the water molecules are actually inside or incorporated in some kind of stoichiometric ratio within the crystal structure. Glass, too. Did you know, even though this glass looks totally dry, we call this wet glass. You know, why is this wet glass? It's wet glass because the surface of the glass is highly polar. And so water molecules in the air can get stuck on the surface of this here. And so even though you can't see them, we call this wet, and there's just a tiny, tiny bit of water on here. So people who work with water-sensitive chemicals, you know, there are a lot of water-sensitive chemicals, chemicals that you don't want water around, otherwise they'll decompose, like calcium carbide, for example, others. All those, what we do with the glassware is we put it into a drying oven, and we dry the glass first. But you take it out, immediately when you take it out of the drying oven and you let it cool in humid air like this, what's going to happen? It's going to resaturate with water. Well, fortunately, our chemicals aren't too water sensitive, so we aren't going to worry about the surface absorption of water on the glass. Just ignore that. We will worry about fingerprints, so you want to wipe off any fingerprints before weighing. Like this, so you get some consistent masses. However, you know, this is a fine powder. And one of the first things in your procedure is you're going to obtain an unknown, you know, from the stockroom. And so we want the unknown number. A lot of people don't write an unknown number for some reason or other, you know. But we need an unknown number. And the first thing is, okay, what does the unknown look like? And so the unknown number is in your observations over here. And so what does your unknown look like? Is it a black tar? Is it a brown solid? What does it look like? Well, your unknowns are probably going to look like a white powder. Powders are very, very tiny crystals. And so it just looks like a fine powder. I think everybody's unknown looks the same, although everybody's unknown will contain a different amount of sulfate. And so over here we want to write our observations like you know, color, form, masses, amounts, any changes in appearance, that kind of stuff. Okay, but this is what we call, they aren't really wet, but this is what we call, our unknown looks dry, but it really isn't dry. Why? Is our unknown not really dry? Even though it might look dry, it's not dry because this is a repetition. Surface absorption of water. And so what we're going to do is we're going to dry these samples. In fact, they're going to put them in the oven the day before our lab. We'll put the lid under here, and these are going to be dried. And so it says in the procedure, it says to obtain the dried unknown sample. We got it. you know, from the oven. Here we might write, you know, what was the temperature of the oven? You know, I don't know. You can look it up. There's a thermometer above the oven next behind us here. 114 degrees C overnight. Dry. These are the observations that we take. We don't start really analyzing the data until much later. We're just taking observations now. The problem is when you remove this from the oven, what's going to happen? It's going to resaturate. Well, we have a way to prevent resaturation. This is how we prevent resaturation of water in our unknowns. We have a sealed glass container. This is the lid here. I'm going to hold it from the lid and hopefully the bottom doesn't fall off. The bottom doesn't fall off because of the vacuum that's created. And plus there's a sealant here, there's grease. So in order to get the lid off, you aren't going to pull the lid off. No, be careful, don't do this because it might pull off. You slide the lid off. That way you don't have to create a vacuum. And so in here is just air, right? But stuck at the bottom of this is what we call desiccating agent or desiccant. This is good desiccant. This is bad desiccant. This is bad desiccant because the color changed. There's a color indicator here depending on how much moisture the desiccant is absorbed. And so this desiccant needs to be regenerated. Do you know how we regenerate desiccant? Desiccant is a hygroscopic solid like calcium sulfate, which forms hydrates. And so the waters get incorporated into the crystals here. And then there's a coloring agent here, some copper compound that changes color depending on how much water hydration it has. And so this desiccant is it's easy to regenerate. We just reuse it over and over again by just throwing this in the oven. When we throw this in the oven, it's going to drive all the water out of the crystal, off the surface of the crystal, if you get it hot enough. Right? And then it's going to look like this again. Okay, with the desiccant in here, that means any water molecules in the air here, when they strike the crystals here, they're going to be absorbed either on the surface or absorbed into it. And so what we have is we have dry air inside here, hopefully 0% humidity. If I keep opening this and leave it open, obviously a lot of humid air is going to get in there. It's going to take some time. And so, I don't know, a lot of people do this. Maybe they don't get the concept of desiccant, but they just sit there with the lid off, for like 5 minutes, 6 minutes, the lid's off, and I'm thinking, what are they thinking? What are they thinking? Because it's going to take time to dehumidify the air, right? This is wasting time. And so you only take this off for since this is bad anyway, you only take this off for short periods of time. Put your sample in there, immediately put the lid back on. You don't sit there and wait. Even though I say this every semester, somebody always does it anyway. I think, okay, so we'll put our sample in there, but the sample is going to be hot out of the oven. You got a hot sample there. You got to handle it with tongs or paper towel so you don't burn your fingers. There's hot glassware. Does hot glassware look any different than cold glassware? No, it looks the same. So you can't tell if it's hot or not. You can feel around it and see if it's hot. But at 114 degrees C, you don't want to be grabbing it. It'll cause like secondary burns maybe. So be careful with that. Well, when you get your sample, we have this. We have a ceramic plate, so you don't have to hold it in your palm. And we have some tongs. You have tongs in your drawer. They're called crucible tongs. Like this. The weighing bottle is small. I didn't get a sample. And so you can just hold it like this. Walk it back over here. Okay, then when you put it inside here, what you do is with your tongs, you grab the edge of it like this. Why don't we want to handle, well, it's hot. You don't want to handle it with your fingers, right? And so grab the edge of it like this, and then place it in the desiccator. But what about the lid? The lid's still going to be on the plate here. Do we want the lid to be in the desiccator too? Yes. We want the lid to be in the desiccator because we don't want it to resaturate with water. And so we grab the lid. And we don't have that many desiccators. So this is what you're going to have to do. You're going to put the lid in here and then put the weighing bottle inside the lid to make room. We could fit 3 or 4 samples in here. Everybody has to share. Okay, now with the hot air, what happens with hot air? Hot air, according to the ideal gas law, hot air expands. As it cools down, what happens? It contracts, right? And so if we put 3 or 4 in here with hot air, sometimes we create quite a big vacuum because as it cools down, it contracts a little bit. And so it says to leave the lid ajar. It says to leave the lid ajar, meaning just a slight air gap there. It says for 5 minutes, but 5 minutes is too long. You know, by 5 minutes, it's probably already down to room temperature, close to it, right? And so just for a minute, maybe, leave it ajar and then seal it like this. We have our samples there. All right, then we seal the lid. You know, this is just so we don't create too much of a vacuum, and then let it cool down. It says let it cool down for 10 minutes, but maybe 10 minutes is overkill. Maybe another 5 minutes on top of that, so it's close to 10 minutes total cool time. Well, anyway, what's going to happen if we remove the weighing bottle? Now I want to go weigh my samples out here. What's going to happen if I remove the weighing bottle out of this? It's going to resaturate, right? And so how do I prevent resaturation from occurring? How do I minimize resaturation of the crystals, the moisture? How I minimize the process of resaturation is this. When I remove this, there's dry air above here. And then what I'm going to do is I'm going to quickly grab the lid and then put it on top. Since it's already cool, I could just remove the weighing bottle. You could just grab it with your fingers. Remove the weighing bottle with your fingers, grab the lid, and put the lid on top. Like that. That way you trap dry air above your sample. Then you go weigh it. Ignore the procedure. The procedure says to weigh out the weighing bottle. Why are we weighing the weighing bottle? Why are we not weighing the weighing bottle? I'm going to say this. I'm going to say this 2 times this semester. Maybe I said it 1 time last semester, and a lot of people were weighing the weighing bottle. So I'm going to repeat it. Why are we not weighing the weighing bottle? Because we could zero the beakers. We don't need to weigh the weighing bottle. Okay, so I'll repeat it. Why are we not weighing the weighing bottle with sample? Because people who weigh the weighing bottle and the samples end up taking the balance for a long time. And we have a lot of students in this class. And those people are wasting other people's time, basically, by weighing the weighing bottle. And so I have to go in there and explain to them what to do, you know, because they didn't quite catch it during the pre-lab. And so we don't need to. That's why we aren't weighing the weighing bottle. And since we aren't weighing the weighing bottle, we don't care about fingerprints. You can handle this with your fingers, right? The beaker, we are tearing that, so you don't want to handle it with your fingers. And so you tear the beaker, open the door, remove the lid, and then tap out some of your sample into the beaker. And then what should you do with the lid to the weighing bottle? Leave it off? I go there to the balance room and I see people with the lid off and the weighing bottle here, and I'm thinking, what are they doing? They didn't catch anything, you know, and it happens because, you know, a lot of people are zoned out. or thinking about something else, and so they don't quite catch. And in fact, I don't know, some professor, I was taking one class and some professor says, some students don't catch 90% of what he says in lecture. And what he did, this was a chemistry class I had, it was a very small class, there were only like 8 students there. And so he'd walk around and start reading everybody's notes and he'd just spend like 5-10 minutes just walking around doing that. So all of a sudden I got self-conscious about my notes and stuff like that. But yeah, he's just to prove his point. But anyway, please catch this. This student leaves the lid off the Wang bottle. The Wang bottle's open here to air, and they're just doing something. They're talking to somebody. They're doing something else. What are they doing wrong? Why was I thinking this guy doesn't know anything?
They're letting it resaturate?
They're letting it resaturate. Right? Obviously, poor technique. So anyway, you only take the lid off for a minimum amount of time, just enough to tap it, so we don't get any errors that way. And then some people try to get the exact mass. So sometimes I see them taking the beaker out and then just trying to scrape some of the crystals into the garbage or back into the Wang bottle because they overshot it. But how much do they overshoot it by? How much are you allowed to overshoot it by? It's a lot, so very few people will overshoot it. If you go way beyond that, then then we have trouble. All right, so you do 3 samples. You can do these quickly, one after the other. We got the 3 samples. Once you have the dry weight, should we seal the beaker? Do we need to seal that beaker? No, once you have the dry weight, then who cares if it gets resaturated, because we know what its mass is dry, and we can always throw it in the oven and we call it anhydrous. Anhydrous is without water. The anhydrous weight of this, or anhydrous. All right, so when you do the procedure here, do you just copy down the procedure from your lab manual verbatim? No, you shouldn't do that. What a lot of people do is they just draw pictures, Draw pictures like you have this, put it in a desiccator, 10 minutes or something like that. Okay, maybe I only put it in 8 minutes because it's probably cool enough. And then weigh out 3 samples like this, And then write the ideal mass. The ideal mass, I don't know, 0.1, let's say the ideal mass was 0.1 thousand grams. Are you going to get exactly 0.1 thousand grams, you think? No, anywhere. And so, sample 1, you have to mark these beakers, otherwise you don't know. And people get them mixed up all the time. 1, 2, and 3, some marking on there. And so sample 1, let's say, was 0.9959 grams. Is that close enough? Is that close enough, or should they try to tap in some more samples? Yeah, that's plenty close enough. Let's say sample 2 is 0.1185 grams. Should they try to remove sample? 0.1158 grams. Should they try to remove sample? They got way too much? Yes or no? No, that's within 20%. And then sample 3, they started getting a little lazy and sloppy. 0.1659 grams. Is that close enough? 0.165. The target was 0.1 thousand grams. They got 0.1659 grams. Is that close enough? No, they blew it on this one. What do they have to do? They have to do this one over again, basically.
Just to clarify, so you want us to write a table of contents like on the first 2 pages?
The first 1 or 2 pages and leave it blank for right now.
And by the end of the semester, we're just going to fill it in.
You're going to fill it in at the end of the semester.
And then you want us to do pre-lab before every lab?
Yes.
Okay.
Pre-lab before every lab.
And you don't want us to write it right on the back of the page, just 1 page?
Yeah, just on one side. You have plenty of pages, so just on one side.
Even on the pre-lab?
Yeah. You know, uh-huh. Yeah. You don't have to draw a picture. You could write it out. Or you, if you want, you could just write the whole thing verbatim. But if you write the whole thing verbatim, like, it's going to take way too long. What you need to do, well, you don't really need speed just yet. When you get into organic chemistry, you need speed. Otherwise, you don't finish. When I took organic chemistry, there was a 5-point penalty for each second you went overtime. And so if you didn't finish, you know, within time, then you were out of luck. You know, if something went wrong, that was out of luck. That was for organic. When I took physical chemistry, they had open labs because nobody ever finished on time. And so they made extra labs so people can come in when they were free to finish the experiment because the experiments were so long. You know? And so it depends on what class you have. But speed is key for a lot of classes. Well, anyway, things go wrong in lab, and sometimes you have to repeat. So this little error here cost, I don't know how many minutes extra, you know, but some extra time. And so this one was no good. It's too much. Too much sample means, you know, rather than using a 600 milliliter beaker, they got to go to the 1.5 liter beaker. Make it work, and so it's too big, too much. You know, too little is no good too, because it's hard to detect. You know, in small quantities like trace contaminants are very hard to detect, right? And so you want the maximum, the biggest size sample, without having to go to excessively big glassware. All right, so just have some written procedure, and over here we're going to write, you know, what we actually did. We aren't going to really think about the analysis of the experiment just yet. All right, let me just quickly say something about today's experiment. Today's experiment, we're going to be weighing samples of water. Weighing samples of water on a centigram balance is easy. Weighing samples of water on a 1/10 of a milligram balance is a pain. But do you know why weighing a sample of water is a bit of a pain on these balances? Uh-huh. You know what? If you're putting in drops and you overshoot, no big deal. Rather than 10 drops, you write down in your observations. Like the procedure says 10 drops, I put in 15 drops. I don't care because that you can work out later. You just write 15 drops in your observations. So overshooting drops is no big deal in this experiment because we're getting the volume per drop. So you're going to have a bigger volume, but you have more drops, so you get the same. It's a intensive property, not an extensive property. Some things that deal with extensive properties, then it would be a big deal. You know, but that is no big deal. Why is it such a pain to weigh water? It's such a pain to weigh water because the balance, you know, what happens with water? You put some water in here, by tomorrow, by the next day, the water volume decreases until it's all gone because it's evaporated. And so if you put a sample of water on these balances, you're just going to watch it evaporate as the mass is going to drop. You know, maybe it won't all evaporate. What you do is you'll saturate the inside compartment here. Once this has reached 100% relative humidity, what does that mean? 100% relative humidity. 100% relative humidity means, can you get more humid than 100%? Is it possible to go 120% relative humidity? No, once you hit 100% relative humidity, then it's going to stop. net evaporation is going to stop. This is what we call a dynamic equilibrium. So evaporation never stops, but you have condensation occurring, and the evaporation and the condensation rates are equal, and so the mass stabilizes. Are you going to wait for this to reach 100% relative humidity and the mass stabilize? That's like if you go to the indoor swimming pool, it's really humid in there. Maybe they've reached 100% relative humidity. But are you going to wait for it to reach that? No. You know, what's the relative humidity today, do you think? 20%, something? 40%? No. But it's not 100%. And so how do you slow down the evaporation process, or how do you minimize it? Well, you don't want to saturate a big volume, but we could saturate a smaller volume. And so that's why we have these watch glasses. We put a watch glass on here, and then we don't have to saturate the entire container. We just saturate in here. Actually, we don't even have to saturate in here. This is going to help prevent evaporation from leaking out here and contain everything, right, to give you a stable mass. And so whenever we weigh water samples, right, we cover them with a watch glass. Now we're weighing water samples in flasks like this. What's this flask called? What's this flask called? This is an Erlenmeyer flask. And so we weigh a water sample like this. We'll put a small watch glass on there. This is what, about a 65 millimeter watch glass, you say? Yeah. Do all Erlenmeyer flasks weigh the same? No. There are no two Erlenmeyers that weigh the same mass. Each one's individual. So you have to number them. This one's number 2. Do all watch glasses weigh the same amount? No. And so this one's number 2 to match. Don't get them mixed up. Otherwise your masses are going to be crazy. And so we're going to have matched Erlenmeyer's, matched watch glasses. Do you want to grab these repeatedly with your fingers? No, because we're going to be weighing these. And so we're going to weigh this empty mass of the flask plus the watch glass, and then we're going to add water sample, reweigh it. Not only are we going to add one water sample, we're going to actually add 2 water samples. And so we're going to add 1 water sample, reweigh it, and then leave it there. Then we're going to add another water sample and weigh it again. So we could figure out the masses of those. All right, I didn't expect anybody to have read today's experiment, so we're going to discuss the whole thing. But for Thursday's experiment, read through that, the procedure, so that you can come in prepared. It's important. I know that sometimes, like the traffic situation or whatever else, you might come in late. But if you make a habit of coming in late, then I'm going to start deducting points right off, or I'm going to prevent you from working in lab that day, because at the beginning of lab we have the safety. I'll try to hold off on the safety discussion until near the end, but try to come in on time. I understand you can't always come in time, and you don't want to get a speeding ticket just to come in on time. It's not worth it. But come talk to me about your particular circumstances, because we got to get started right at 9:30 on Thursday. So try to come in on time on Thursday. Don't be late, because I'm going to talk about some safety stuff. Okay? And if you miss the safety discussion, then, at UCLA, they just lock the door. And you come in late, you're out of luck. You have to go to a makeup session. They don't care. Actually, they don't care, because they don't care about retention rates, about all this stuff that we're supposed to care about here. If you fail, you drop out. Well, like my friend, they really didn't care that they kicked him out. I think, well, maybe they care because they gave him second chance and a third chance, but he had to pay a lot of money for those. Going through extension. Extension was really, really expensive. But anyway, let's take a break, and then we'll talk about the procedure for today's lab.